Welcome everyone to this virtual Mile High 2020 presentation. My name is Daniel Silhavy. I'm a project manager and OTT architect at Fraunhofer Focus in Berlin. And today I would like to talk about deep encode, machine learning for per title encoding. So the first question you might have when reading the title of the slides is, where does the name deep encode come from? So this does not only sound very fancy, which is beneficial for us, but it also relates to the fact that we are using deep learning technologies within our technology stack. Let's start with the foundations of per title encoding and why we need per title encoding. Usually when we stream videos over the internet these days, this is based on a technique called ABR streaming, adaptive bitrate streaming. Adaptive bitrate streaming means that the client is switching between different available qualities during playback, depending on how good the network condition is. Usually we achieve this adaptive bitrate behavior by offering different bitrate resolution pairs to the client. And this is what you can see on the left side of the slide. So in this case, we have bit rates ranging from 235 up to 5,800 kilobits per second, matching resolutions of 320 times 240 and 1920 times 1080. And what you can see on the left side, those combinations are usually referred to as an encoding ladder. And for a long time, those encoding ladders were static, which means regardless of what type of content we were inputting, we always use the same bitrate resolution pairs. So why is this bad, or why is this not optimal? This is pretty much caused by the fact that we have different redundancies or different levels of redundancy in our content. So if you think about how an encoder works, usually an encoder tries to find redundancy in the frames itself or between the frames, and then compress the content or compress the frames, ideally throwing only away not throwing away a lot of information. And if you look at animation movies or nature films and compare that to action movie or sports content, you will see that those types of content differ in terms of complexity and differ in terms of redundancy. So usually in action movies, you have a lot of movement as well as in sports content. But in animation movies, there's less movement and there are large areas which can be encoded pretty easily. Essentially, this leads us to the conclusion that different content requires different encoding settings. And then if we use a tailored encoding ladder for each types of our content, we can pretty much optimize in terms of quality, and we make sure that we don't waste any bits on the specific type of content. And this is where per title and per scene encoding come into play. So the goal of per title encoding is to change the encoding settings or change the bitrate resolution pairs based on the content itself. This means we have one tailored encoding ladder for the entire video. The downside of per title encoding compared to something like per scene encoding is that we do not account for complexity changes in the content itself. So usually the content itself has different scenes, and those scenes also differ in terms of complexity. And when you use something like per scene encoding, you can pretty much change the encoding settings for each scene individually. So in the end, with per title encoding, you end up with one tailored encoding ladder. On the other hand, per scene encoding, you have multiple encoding ladders for each part of the video, so for each scene. So per scene encoding compared to per title encoding offers the advantage that you account for the complexity changes in the content itself. So how does per title or per scene encoding work? What I'm showing here is the standard approach for per title and per scene encoding, because what you usually start with is some kind of complexity analysis. And usually this step is done by doing a lot of test encodes with different settings. So this means different quantization parameters or different target bit rates. And you calculate the corresponding VMAF and PSNR values for the respective bitrate resolution pairs. And from all those values you gain here, you can calculate something called a convex hull. The convex hull is kind of the big buck bunny of per title encoding. So pretty much in every per title encoding talk, you will hear the term convex hull. And mainly because that's the reason, or that's the technique we can use to derive the optimal bitrate resolution pairs. So those bitrate resolution pairs you want to have in your encoding ladder, they are located on the convex hull or very close to the convex hull. And based on those values and the per title encoding ladder you can derive from that, you can do your production encodes like you did before with the static encoding ladder. And this is what you also will see in a lot of talks. So this is a visualization of the corresponding bitrate VMAF pairs for certain resolutions. And I don't want to go into much detail here, but the convex hull I'm talking about is depicted here in yellow. This is the line you can see, and I'm trying to show that with my mouse pointer, which pretty much spans here and covers all the relevant data points. The downside of this approach is that you need a large amount of test encodes in the complexity analysis step. And this can become very computational heavy and also very expensive. So how can we optimize this approach? How can we perform a complexity analysis with less encodes or even without encodes? And this is where machine learning comes into play. So what if we replace the first step, the complexity analysis step, with machine learning-based predictions? So what we are trying to do here is we predict the mandatory bitrate VMAP pairs for all the resolutions using machine learning, and then the steps after that remain the same. So based on the predictions we are doing, we are calculating convex hull, we are selecting the optimal bitrate resolution pairs from that convex hull, and we do the production encodes again. So we can use machine learning-based predictions to avoid the test encode and still derive a sufficient amount of data points to calculate the corresponding convex hull. So how does a machine learning-powered per title and per scene encoding workflow look like? We start off with a source video. This can either be live or VOD, and we feed that source video into the distribution workflow. And there we start with a scene extraction. And depending whether you want to do per title encoding, which will result only in one scene, or per scene encoding, we extract multiple scenes from the source video. All those scenes and the source video itself are fed into a complexity analysis component. And this complexity analysis component is deriving various information from the source file and the videos from the video itself. This means something like the resolution and the frame rate of the video, and also color and brightness information, as well as spatial and temporal complexity values for each scene or the source video itself. All those information serve as input for the machine learning model. And I want to go a step back here and mention that the machine learning model itself obviously was trained on a large amount of test encodes. So in order to have this machine learning model in place, we needed to do a lot of test encodes, we needed to do a lot of complexity analysis to derive a sufficient amount of data, which we can then use to predict VMAP PSNR values for predefined bitrate resolution pairs. So pretty much the same thing, which would also be falling out of a standard complexity analysis component doing a lot of test encodes. So the machine learning model gives us the VMAP and PSNR values for our bitrate resolution pairs, and those serve as an input to the convex hull calculation. And in the end, we end up with an optimized tailored encoding ladder for the specific title or for the specific scene, which we feed into the encoding packaging pipeline, which then deploys our data or files on the CDN. And then they are delivered to the video player via the CDN. One thing I didn't mention so far is the feedback loop from the video player itself. Because during playback, you can derive certain quality information from the player itself. This gives you a lot of useful information. So for instance, in a simple scenario, this means that maybe 90% of my clients are streaming higher than 3 megabits per second. This can again serve as an input for the machine learning model or the component which is deriving the optimal encoding ladder in order to have a context-based per title or per scene encoding ladder. So how does the machine learning powered part of the solution look like? And in general, when you want to predict a value like VMAP or PSR, this can be classified as a regression task. And I want to introduce 5 different models which we used during the development of the solution. We started with the logarithmic model, which is pretty much a model we used in the POC. This one is easy to implement and train, but it does not really reflect the complex relationship between the different parameters we are inputting. So this one usually gives you a very high root mean squared error. Next one is the feed-forward neural network. This one is robust enough to support missing input values, which is good because you cannot derive all values from each source video. And it's prone to overfitting issues. On the other hand, it requires a large amount of data for better performance. So since we keep encoding and keep deriving all the information we need for prediction, this one is getting better and better. Next one is the convolutional neural network, which is flexible and video friendly in terms of the processing, but it's very computationally expensive. So the training process can take quite a lot of time. Next one, XGBoost, does not require as much normalization for the training attribute. So this is good. This can be trained very fast. But certain encoding methods can weaken the model performance. Last one, the stacked model, is very flexible in terms of its concept in combining basic to advanced models. This is also the one that gives us the best root mean squared error. But due to its complexity, each model might require several cycles and fine-tuning in order to perform well together. So all in all, those are the 5 models we trained so far, but we're actively working on new models and obviously also fine-tuning the existing ones. So at this point, I want to show you a small demo because I think that's much better than covering everything in theory. So I'm showing a video here. And this is a video of a per title encoding demo workflow. So we start off with selecting a video and uploading this video. This might take some time depending on the video size. Obviously, if you host such a solution on premise, this computation time or this uploading time is not needed because you would share the same file storage for the solution and the videos you want to encode. So in this case, the upload is successful. We wait a moment. And at this point, I want to pause because here we have the opportunity to actually define a certain range of video bit rates we want to use in the final encoding ladder. Also a certain factor, so how far apart are those video bit rates, and the corresponding VMAF score. So we are targeting a video bit rate from 1 megabit to 4 megabits in this case, with a factor of 1.25 to 1.75, with target VMAF values between 40 to 93, and the VMAF distance, so the quality pairs or encoding pairs we are using in this encoding ladder in the end should be at least 6 VMAF points apart from each other. Let's continue with the video. So we start the task. And at this point, multiple workers are doing the processing, the characterization, for instance, and also deriving the information I mentioned before, the complexity information we use for prediction of the corresponding VMAF values. So when this is done, we get the predicted encoding ladder. We can even switch between different available regression models, basically the ones I showed you before. And we can compare it to a static encoding ladder. So we're using a static Apple encoding ladder in this case to compare the predicted encoding ladder or the per title encoding ladder to. So if you continue here, you can see that we are plotting those values, but this is pretty much the output I mentioned before. We have a predicted encoding ladder, we have a reference encoding ladder, and we can use this predicted encoding ladder to actually create the final encodes in the end. And as you can see, this is pretty fast. And our main goal was to avoid the test encodes in order to derive this encoding ladder, which we did in this case successfully. Okay, let's switch to the next slide then. Another demo slide. I want to show you that this approach also works for Persine encoding. And what we will see in this video is a live stream encoded with 2 different encoding ladders. On the left side, you can see the standard encoding ladder going up to 7.8 megabits. On the right side, you can see the Persine encoding ladder. And during playback of the source file and during encoding and packaging, we are adjusting the Persine encoding ladder. And in this case, we are doing that using MPEG- with a multi-period approach and a standard -JS client. And if I start the video now, you can see that both videos are playing, and the left encoding ladder has less resolution bitrate pairs compared to the one on the right, compared to the Persine encoding ladder. And you can also see that the Persine encoding ladder, if I pause again, goes up to 3 megabits, while the static encoding ladder goes up to 7.8 megabits. We are also only using a resolution of 720p in this case, which is sufficient because this already gives us a VMAF quality of approximately 93, which the target algorithm in this case is aiming for. So as you can see during playback, the encoding ladder switches. So we have a new period in the -MPD, and this period contains different resolution bitrate pairs than the one before. And that's how we achieve the Persine encoding workflow. So we are pretty much putting each scene into a dash period, and the dash period itself can change the resolution bitrate pairs. And the client is adapting to that and plays over the periods as it would in a single period approach. we scroll down a bit, we are also showing the bitrate graph, which is not too interesting in this case, but also gives you an indication that the per title or per scene encoding ladder uses less bits than the default encoding ladder. And also on the right side, we can see the currently predicted encoding ladder. At this point, I would like to share some concrete results with you. So the following analysis is based on a partnership with one of our customers, and they were still using a static reference encoding ladder. And they provided a test asset and asked us, okay, can you please optimize this in terms of storage and delivery costs, but ideally maintaining the same quality as before. And this is what we did with the deep encode solution. So as you can see, like before, we have the same amount of resolutions ranging from 432 up to 720p. The bit rates are comparatively low if you compare that to static encoding ladders in general. So we're starting with 240 in this case and going up to 980. This is below 1 megabit, so this content was really easy to encode. The corresponding VMAP values for all of those bit rates are depicted in the third column. And as you can see, we mainly achieved a VMAP gain. So especially for the first two representations, we could even improve the VMAP score, although we decreased the bit rate. We lost a small amount of the VMAP values on the 540 quality, but the VMAP quality for the 720p resolution remains the same. And the storage size is also reflected in terms of the bit rate. So whenever you decrease the bit rate, obviously the storage size also decreases. So as I said, we mainly achieved the goal here. So we limited the storage size and the delivery costs, and a concrete number is given on the table below. So before it was 1,872 megabytes, and now it's pretty much cut in half. We gain 53% in terms of storage savings, and also obviously depending on which quality is played the most, this is also reflected in the delivery costs. Two things I want to mention here, or two specific aspects which caused this effect and which made this possible, is that you know exactly which resolution is optimal for which bitrate when you tailor the encoding settings, which is why in this case we could start with a resolution of 768 times 432 with a comparatively low bitrate. And in this case, we also knew, okay, we want to achieve 83 VMAP points. This can already be done at a resolution of 720p with a bitrate less than 1 megabits. So by tailoring this encoding ladder, we could cut storage and delivery costs in half. Second thing I want to mention is that you should not, or we should all not take this for granted, because obviously, depending on the input content, this might look totally different. So if this is a very large or very heavy test file, very hard to encode, those values would change dramatically. So I don't really like solutions claiming that you always save like, I don't know, 30 to 40% in terms of storage and delivery. Obviously, those values depend on what you put into the solution and also what you're aiming for, what your target is. If you want to improve quality, you might end up with an encoding ladder which uses even more bits than the static one before. Okay, this already brings us to the summary and the outlook part. So what we saw today is that a lot of customers and a lot of content providers still use conventional static encoding ladders, which means they apply the same encoding ladders for all types of content. In the worst case, this leads to increased storage and delivery costs, a waste of quality, and no optimization for complex content. Conventional per title encoding tries to solve these problems by doing a lot of computational heavy test encodes based on the source file, and then derive the optimal encoding ladder for the specific file. Conventional per title encoding also doesn't account for complex scenes within a movie. The solution we are proposing is a machine learning powered per title and per scene encoding solution. So in this case, we don't do any computational heavy test encodes. We rather extract metadata and use this metadata to perform ML or AI-based predictions. So we are categorizing the content, we are labeling it, we are deriving certain metadata information. We are also doing an automatic scene change detection, and all this information can be used to feed into a machine learning component, which predicts the required and necessary PSNR VMAF bitrate pairs and derives the optimal encoding ladder using those predictions. Enhancements are per scene and context-aware encoding. As I mentioned, per title encoding only covers half of the medal. You would also need to encode or optimize for specific scenes in your video. And you can even use information coming from your streaming client, from your streaming player, to enhance this prediction or enhance the selection process. So for instance, if you have customers, or 90% of your customers are streaming at a certain bitrate, you can use this information to tailor or optimize your encoding level even further. For future references or for future enhancements on our solution, we are also exploring additional video features and want to enhance the mechanisms or models we are using with additional data. Thanks for your attention. So if you have any questions, I will be available now, and yeah, looking forward to your questions.